This next section we're going to talk about half-lives. We mentioned that radioactive isotopes emit particles, so they decay. They either undergo alpha decay, beta decay, positron emission, and when they do that, we've noticed in those reactions that they become a different element, and they are no longer, much of the time they're no longer radioactive. The other element might be radioactive as well, but the original element is no longer there. So here we have this reaction still showing on the screen. We start off with some aluminum, and then the answer to that was that we got some phosphorus at the end. So this amount of aluminum that we have is becoming phosphorus in this reaction. So we no longer have our aluminum. And the rate at which the aluminum is disappearing can be described by this half-life. So we have an amount of time. A half-life is just an amount of time, and that's the amount of time it takes for half of the sample to change into something else, to decay. So here I tried to graph this a little bit. It's not a line, a linear straight line, but it's a curve that happens when you are following the amount over time that you have. So on the bottom I have the half-lives written here. If we start at time being equal to time 0, after one half-life has passed, we have half the amount. So we started with 8, whether it's 8 micrograms or 8 microcuries worth of activity, whatever the amount is, 8 of it. After one half-life, we have 4 of it. So we have the 4 over here. I put this dot over here near the 4. After 2 half-lives have passed, half of 4 is 2. So I put this dot over here near where the 2 is on that y-axis. After 3 half-lives have passed, now you have 1 because half of 2 is 1. Then the next half-life, half of 1 would be 1/2. So I don't really have that marked on the axis over here, but that would be 1/2. And then this, after 5, we would have 1/4. So 5 half-lives took us from 8 to 4 to 2 to 1 to 0.5 to 0.25. So that is a curve that it starts off very quickly and then it sort of slows down as far as the rate of disappearance. So what we're going to do with half-lives is do some conversions because it's a unit of time and we should practice doing unit conversions. So you can convert half-lives into days, into hours, weeks, depending on what sort of unit of time you have. Let's take a look at that. So for this first example, we are told that we have a certain radioactive isotope, iodine-131, and that the half-life is 8.0 days. So one half-life is 8.0 days. That 8 is a relationship. We're being told that one half-life is equal to 8 days. So this is not what we're trying to convert. This is the relationship. Now we are told that 3.5 half-lives have passed for our sample. And then we want to know how old is it in days. So this 3.5 half-lives is the age of the sample in half-lives. We know how old the sample is in half-lives. We have a sample that is 3.5 half-lives old. 3.5 half-lives have passed. So it is 3.5 half-lives old. We want to know how old it is in days. So what this is a conversion problem. The age of our sample is 3.5 half-lives. We want to take that age and convert it to days. We want to know how many days old is it, not how many half-lives old is it. So let's go ahead and do this conversion using the relationship that we know. All right, so I'm going to abbreviate half-lives as HL. It is 3.5 half-lives. And then our conversion factor is up here. One half-life, let's put that in the denominator. One half-life is 8.0 days. We'll abbreviate that as D. When we're doing this conversion, we can cancel the half-lives, and then we'll end up with days. And it looks like it is 28 days old. So for 28 days, in 28 days, 3.5 half-lives have passed. It's the same interval of time, 3.5 3.5 half-lives is equal to 28 days, just like 1 half-life is equal to 8 days. So different radioisotopes have different half-lives. Now we have a different isotope, radon-222, and for this particular radioisotope, 1 half-life is equal to 3.80 days. So this one decays a little bit more quickly. 1 half-life is equal to 3.80 days. Now we have a sample of radon-222 that is 1.50 weeks old. So that is the age of our sample in weeks, and we want to know how many half-lives this is. So we're doing the opposite here. We have our age of sample being 1.50 weeks, and we want to convert that into half-lives. So let's go ahead and take that 1.50 weeks, and we'll use this relationship to make a conversion factor. And we have this relationship over here. We don't know how many weeks our half-life is. So we're going to need another conversion factor to convert weeks into days. Then we can convert days into half-lives. So let's use this relationship first. 1 week is 7 days. We'll put the week on the bottom and the days on top. So once we multiply that by 7, we'll have the number of days. Now we can use this relationship, this first relationship, to convert days into half-lives. We're going to put 3.80 days on the bottom, and we will put 1 half-life on top. So when we do this conversion, we will cancel out the weeks and we will cancel out the days. Let's take a quick look at significant digits too. Our original measurement of the age of the sample is 1.50 weeks. We have 3 significant digits there. 7 days in a week is pretty much defined. We'll say that that is exact. And then the half-life we know to 3 significant digits. We don't know if it's 3.802 or 3.800 or 3.799. So this is also 3 significant digits. So I think we can keep 3 in our answer for the number of half-lives that have passed. And when I do this, I get 2.76 half-lives. Okay, let's try one more of these conversions. The half-life of the metastable version of technetium is 6.0 hours. So this one is even shorter half-life. It reacts more quickly. Let's go ahead and write down that relationship. 1 half-life is 6.0 hours. Now what do we know? That 6.5 half-lives have passed for the sample. So it is 6.5 half-lives old. You can say that if 22 years have passed for someone, that they are 22 years old. So this sample is 6.5 half-lives old. So our age of sample is 6.5 half-lives, and we want to convert that into days. All right, we have a relationship to hours, so I think we should write down another relationship that can relate hours to days so that we can do the conversion. So 1 day is 24 hours. Now we can do our conversion. We have 6.5 half-lives. We know that 1 half-life is 6.0 hours. So we'll put the half-life on the bottom. We'll put 6.0 hours on the top. And now we want to know days, so we'll put 24 hours on the bottom, 1 day on top. This will cancel the half-lives. It will cancel the hours, and we'll be left with days. It looks like we have 2 significant digits in a lot of these, probably more than 2 for that. I think that is defined. So I'm going to round the answer down to 2 significant digits after I multiply this, and we have 1.6 days. So about 1.6 days is what it takes for 6.5 half-lives to pass by. Those are equivalent ages. 6.5 half-lives is equal to 1.6 days for this particular isotope. All right, so we mentioned that the half-life is how long it takes for half the sample to disappear. So the amount of sample that you have, whether you're talking about mass or the amount of activity of the sample, it gets cut in half every time a half-life passes. So another thing that we can do with this half-life is figure out the number of half-lives that have passed, and then we multiply the original amount by half that many times. Kind of like the graph I showed you at the beginning of the video. After one half-life, you have half your sample. After a second half-life, you have half of that. So you keep cutting it in half, the number of times equal to the number of half-lives. So n is the number of half-lives that have passed. That's the number of times you have to cut the original amount in half to get the amount that is remaining of your sample. So here we want to know the amount remaining. So here is our equation written out again. The amount remaining is what we're trying to figure out. So we need the original amount. It says we're starting with 344 milligrams, so we have our amount expressed in mass, milligrams. We have 344 milligrams of radon, and then we are going to multiply that by 1/2 n times. If 4 half-lives have passed, n is 4. So I kept 3 significant digits here just so that we know that we are pretty confident with the number of half-lives that have passed. So we're going to multiply 344 by 1/2 raised to the 4th power, or you can just do this 4 times depending on how comfortable you are with either way. So if you want to put 1/2 raised to the 4th power into your calculator, you can do that. If you want to write it out 4 times, you can do that. And so you're just dividing this by 2 4 times, and that gives us 21.5 milligrams remaining after 4 half-lives. All right, let's try this again with the next problem. So we want to know the amount remaining. This time the amount is not given in milligrams or mass, it's given with an activity amount. We'll be talking about the units of activity in the next video. But microcuries is a unit of activity. So we have 58 microcuries worth of radioactive sample. How much of this radioactive sample will be left after 5 half-lives have passed? So we're going to take the original amount, which is 58 microcurie, that's the original amount, and then we're going to multiply that by 1/2 raised to the 5th power, or we can just cut it in half 5 times, whichever is easier for you. So 1/2 raised to the 5th power, just in case you are curious, is the same as 1/32. But however you do that, you should end up with 1.8 microcuries as what is left after 5 half-lives have passed. We divide it by 2 5 times, so that makes the number pretty small pretty quickly. All right, for this last example, we have a slightly more involved example. So here is our equation. We want to know the amount remaining, how much activity will be left after 3.75 days. So that is the amount remaining, the amount that will be left. So our original amount is 268 microcuries. Again, this one, the amount is given in activity, microcuries worth of activity rather than milligrams or micrograms worth of mass. So this is the amount. And then we want to multiply it by 1/2 raised to the n power, where n is the number of half-lives. So we need to know how old the sample is in half-lives, and we don't. We just know that the sample is 3.75 days old. This is the age in days, and we're going to need to convert that to the age in half-lives so that we can put n there. The n is the number of half-lives, not the number of days. So we have to do a conversion first. we were told that 1 half-life is 15 hours. Our age in days that we're trying to convert is 3.75 days. And we need to convert that to half-lives. Our half-lives, we know the hours, so let's go ahead and convert days into hours. So 1 day is 24 hours. So we'll take the age in days, multiply it by 24 hours in a day, and then we will have the age in hours. Then we need one more conversion factor. That 15 hours is 1 half-life. When we do this, the days cancel and the hours cancel, and we will have our age in half-lives. And so I have that the age of the sample is 6.0 half-lives old. So now we know the number that goes here for the n. That is actually 6. I'll go ahead and replace that. So the number there should be 6. So when we divide it in half 6 times, or when we multiply it by 1 over 2 to the 6th power, or divide it by 2 to the 6th, however we do that, we are going to get 4.2 microcuries as our amount remaining.